In this lecture, we're going to look at the chemical level of organization. Now, Dalton's postulate states that each element is composed of extremely small particles called atoms. All atoms of a given element are identical to one another in mass and other properties, but the atoms of one element are different from the atoms of all other elements. Now, atoms of an element are not changed into atoms of different elements by chemical reactions. Atoms are neither created nor destroyed in chemical reactions. Now, atoms of more than one element combine to form compounds. A given compound always has the same relative number and kind of atoms. Now, molecules are two or more atoms chemically joined together. Compounds are two or more different elements joined together chemically. So, if we look at this, this is a molecule, but since it has two different elements, it's going to be a compound. Now, if we had, say, two oxygens come together, and that would give us O2, or oxygen gas, that would not be a compound because it's the same two same two atoms, but it is a molecule. So I hope that makes sense. Two or more atoms together form a molecule. If they are different atoms, that molecule is a compound. And one of the most recognizable, I guess, molecule in the human body would be human DNA. And the human DNA is described as a double helix that resembles a molecular spiral staircase. In humans, the DNA is organized into 46 chromosomes. And we'll take a little closer look at this a little bit later. Now, the body is made up of lots of atoms and molecules, and let's take a look at the main elements of the human body. The main elements that compose up the human body are shown from the most abundant to the least abundant, and the top four are going to be oxygen at 65% in the body, carbon at 18.5, hydrogen at 9.5, and nitrogen at 3.2. So those are the biggies to really remember, are oxygen, carbon, hydrogen, and nitrogen. The others are also quite important, calcium, phosphorus, potassium, sodium, chloride. They're going to be seen, when we look at cell function. But again, what makes up pretty much the bulk of the mass of the human body is going to be oxygen, carbon, hydrogen, and nitrogen in that order. Now here we see two models of atomic structure. In the planetary model, the electrons of helium are shown in orbits, depicted as rings, at the precise distance from the nucleus, somewhat like planets orbiting the sun. In the electron cloud model, the electrons of carbon are shown in a variety of locations they would have at different distances from the nucleus over time. So again, we commonly see the planetary model, again, where we see the electrons around the nucleus in a ring, again, just like planets orbiting the sun. And then here we would have the nucleus and then the electron cloud that surrounds it. Now, the periodic table of elements is going to have, of course, the list of elements, but it's also going to have the different properties of the elements. Is it a gas? Is it a metal? Is it solid? Is it synthetic? Is it a man-made element? And so on. We're not going to go into a lot of detail about this, but this is where you're going to go to find out quite a bit of information, especially if you go on to take a chemistry class. Here we see the different isotopes of hydrogen. Protium, designated as 1H, has one proton and no neutrons. It's by far the most abundant isotope of hydrogen in nature. Deuterium, designated 2H, has one proton and one neutron. And tritium, designated 3H, is going to have two neutrons. Now here we can use isotopes, the radioactive isotopes, in diagnostic imaging. Here's an example of a PET scan. Here a small amount of radioactive glucose, a sugar, is injected into a vein, and the PET scanner takes a picture of where glucose is being used. PET scanning utilizes a radioisotope tracer that's an analog to glucose called fluorodeoxyglucose. So again, fluorodeoxyglucose. And as it says here, the PET highlights areas in the body where there's relatively high glucose use, which is characteristic of cancerous tissue. And the PET scan shows sites of the spread of a large primary tumor to other sites. And PET, by the way, stands for positron emission tomography. Electron shells. Electrons orbit the atomic nucleus at distinct levels of energy called electron shells. With one electron, hydrogen only half fills its electron shell. Helium also has a single shell, but its two electrons completely fill it. The electrons of carbon completely fill its first shell, but only half fill its second. And then neon is an element that does not occur in the body. It has 10 electrons, filling both of its electron shells. Let's look at bonding. Ionic bonding. Sodium readily donates the solitary electron in its valence shell to chlorine, which needs only one electron to have a full valence shell. Valence shell is the outermost shell. The opposite electrical charge of the resulting sodium cation and the chlorine anion result in the formation of a bond of attraction called an ionic bond. The attraction of many sodium and chloride ions result in the formation of large groupings called crystals. And here we have covalent bonds. Covalent bonds are going to be your strongest bonds. It's going to take a lot of energy to actually break these things apart. And when they are broken apart, typically they release energy. Now here we see a single covalent bond with these hydrogen atoms creating hydrogen gas, H2. Here we have oxygen atoms that are forming a double covalent bond, giving us the gas O2. And here we have a carbon with two oxygens, and so this is CO2, or carbon dioxide, and you can see two double covalent bonds. Here we see polar valent bonds in a water molecule. Now, again, we're going to have our covalent bonds here holding the hydrogens to the oxygen to give us H2O, again, water. Okay, but the way they're positioned, they're going to give us polarity. Okay, and because of the charges of the specific atoms, we're going to get some polarity. And you can see here we have a weakly negative charge and we have a weak positive charge. And why is this important? Because as we know, water is a liquid. Well, what is it that holds these water molecules together to create that liquid and allow us to, say, put our hand down into the water and these molecules move out of the way so that our hand can go into the water? And when we pull our hand out, it doesn't leave a hole in the water, right? It closes back up and, it remains a liquid. Now, of course, this is a different story when we actually freeze the water. Now it's pretty solid, and if we poke a hole in it, say you're an ice fisher person, and you drill a hole into the ice, of course the ice part doesn't fill back in, but that's another story. We're talking about liquid water here. So what happens is we create these hydrogen bonds due to that polarity. So let's look at this again. So again, the opposites are going to attract. So we have the negatives are going to attract the positives. Okay. And the negatives are going to be on the oxygen side. The positives are going to be on the hydrogen side. And so again, this is why we call it hydrogen bonding. Remember, this is a lightly positive charge, a lightly negative charge. It's going to pull it together. So kind of like a magnet. Although I almost think about it more like static electricity, because it's, again, a weaker connection, weaker bond. Okay? And it's easy to pull these apart. And that's why when you put your hand down into water, these will break and the molecules separate until you pull your hand out, and then they pull back together again. Now there's three fundamental chemical reactions. The atoms and molecules involved in the three fundamental chemical reactions can be imagined as words. In a synthesis reaction, synthesis means we're putting things together to form a new product. So here we're taking two components to bond together to make one larger molecule. Okay, so if we look at it as words, if we take note plus book, that combined is going to give us notebook. Notice that note and book are totally different than notebook. So it's a brand new product. In a decomposition reaction, and again, that word decomposition, you think about a breaking down, okay, something deteriorating. Well, in a decomposition reaction, the bonds between the components of a larger molecule are broken, resulting in smaller product. So if we take bookworm and break it apart, we have book plus worm. Now, in an exchange reaction, the bonds are both formed and broken such that the components of the reactants are rearranged. So we can take notebook, we can take worm, and what will happen is note and book will get broken apart, and book will recombine with worm, and now we have note and bookworm. So again, different than what we started out with, but we've just exchanged some things to form a new component here, a new reactant. Now here we're looking at enzymes. Now if we were in a chemistry class, we would refer to these as catalysts. So an enzyme is a biological catalyst. Okay, so enzyme, biological catalyst. And so what do enzymes or catalysts do? Well, they decrease the activation energy required for a given chemical reaction to occur. Okay. And without an enzyme, the energy input needed for a reaction to begin is going to be quite high. And with the help of an enzyme, less energy is needed for a reaction to begin. So you can see here that in order to take these two reactants here and combine them, well, that's going to take a lot of energy for that, to happen. But with an enzyme, we lower this activation energy, and it takes a lot less energy in order to make our product. Okay, and this is extremely important because a lot of our body chemistry relies on enzymes. And enzymes are proteins. And if something damages those proteins, like for instance, maybe a high fever or something, which can actually denature the protein. And what does that mean? Well, proteins are chains of amino acids that have been folded into a specific shape. If we apply something like heat to it, it can start to unfold and totally change its appearance. For instance, if you take an egg, crack it into a hot pan, well, that heat is going to take that clear, snotty stuff and change it into a white, rubbery compound, an egg white. Okay? And so that can happen with the enzymes as well. And just to give you kind of a little better explanation of, what's going on here, I tend to use an example of like my car. Okay. So, if I'm driving home and I have to drive up this hill, but once I get up to the top of the hill, I can coast on into home. Okay. So maybe one day I try and all of a sudden I run out of gas and my car just goes back to where it started. I'm like, uh-oh. So I jump out of the car, I start pushing, and I push it up this far, and no, it rolls back again. And so what am I going to do? Well, I call a friend of mine because he has a bulldozer, and I'm like, oh, this is great. He can take his bulldozer and push me up over the hill, and I can just kind of zoom right in to home. Okay, so I give him a call, and here he comes, and then all of a sudden I realize, wait, he passed me right by, and instead of pushing me, he bulldozed the hill. So now that's going to allow me to actually drive up onto the hill and right down to home. So let's take a look at what happened. So in order for me to get up the hill, I had to exert a certain amount of energy. Okay, well, if my car wasn't working, I could not produce that energy to get to the top of the hill in order to get this reaction going. In other words, get the car rolling and get it home. So my friend with the bulldozer actually acted as the enzyme or catalyst. Now, when I was sitting here and I couldn't move, did he take that enzyme, his bulldozer, pull it up to my bumper, and did we weld it together so now that it's one big machine, and then he was able to, push me? No. An enzyme or catalyst is not used up in the reaction. Okay, it can be used over and over and over again. So it doesn't become part of the reaction. It doesn't get used up in the reaction. So what my friend did was passed me up and bulldozed the hill. In a sense, it lowered the activation energy because I could push it up to this part of the hill and coast on in. So my friend here didn't bother, sticking around once he bulldozed the hill. Where are you going? Oh, that's right. Didn't stick around, right? Took off to go bulldoze more hills and didn't become a permanent part of that reaction. In this slide, we're going to look at dehydration synthesis and hydrolysis. And you can probably tell by the names that it has something to do with water. So in dehydration synthesis, two monomers are covalently bonded in a reaction in which one gives up a hydroxyl group, and that's what we see here. The OH is the hydroxyl group, and the other a hydrogen atom, again, as we can see right here. And a molecule of water is released as a byproduct during dehydration reactions. So think about it, when you're dehydrated, you're losing water. And so we see that in the dehydration synthesis. In hydrolysis, now if we break that word apart, hydro is water, lysis means to break apart. In hydrolysis, the covalent bond between two monomers is split by the addition of a hydrogen atom to one and a hydroxyl group to the other, which requires the contribution of one molecule of water. So here we're actually adding water in, and the OH, the hydroxyl group from the water, goes to monomer 1, and the hydrogen is going to go to monomer 2. Dissociation of sodium chloride in water. Now notice that the crystals of sodium chloride dissociate not into molecules of sodium chloride, but into sodium, which has a plus charge, and so we call that a cation, so sodium cations, and chloride, which has a negative charge, things with negative charges we call anions, and each completely surrounded by water molecules. Okay, so again, if we take crystal salt, we take some table salt, we pour it into a glass of water, stir it up, eventually the water molecules are going to start to surround the individual sodium in the individual chloride, and this is what's going to allow it to dissolve in solution. And again, in order for that to happen, we have to have ionic bonds. And because the sodium has a positive charge, then remember this weak negative charge on the water molecule, that's going to be attracted to the sodium. And then the more positive charge of the hydrogen is going to be attracted to the chloride, which is negative. And again, this is how we're going to get sodium chloride to dissolve.